So, in the previous lecture I was solving a problem of natural convection for you from a fin. Okay. A fin is often something that is attached to the wall of a heat exchanger, and the wall of the heat exchanger is at some temperature T naught and the fluid is at some ambient temperature T f. Okay. And the fin is attached so that the fin has very high thermal conductivity, and therefore, the temperature at the surface of the fin does not vary very much with downstream distance, and therefore, the fin is hotter, and because of that you get a much higher surface area for heat transfer, okay, along this fin. Okay, you get a much higher surface area for heat transfer along this fin. Okay. So, we were considering a fin on the wall of a heat exchanger with temperature T naught, cross sectional area ACS. On the right side the temperature was TL and the fluid temperature was TF. And I told you that the mechanism of heat transfer is heat conduction within the fin, because it is made of a material of very high thermal conductivity, and from the fin to the fluid the heat transfer takes place due to natural convection in the limit of high Grashof number. Okay. And we had done an energy balance for the heat transfer along this fin. The energy balance contains three terms. One is the we did the balance for a differential distance delta x along the length of the fin, and it consists of three terms: energy in at the location x, okay, energy in at the location x, okay, due to conduction along the length of the fin, energy out at the location x plus delta x on the right side. Okay. Energy of that particular differential volume of the fin increases because of energy conduction in from the left, it decreases because of energy conduction out from the right, and also there is a loss of energy due to natural convection from the fin to the fluid. Okay. And we had written these three terms here: the energy conduction on the left Q at x times the cross sectional area, the energy out on the right Q at x plus delta x times the cross sectional area, and energy out on the surface, which is the average flux times the surface area. The surface area in this case is equal to the wetted perimeter, that is the perimeter of this fin, okay, times delta x, that is the surface area on the surface of the fin, okay, that times the average flux due to natural convection. Divide throughout by ACS, divide throughout by delta x, and you get this equation here: minus dq by dx minus 4 times q average by the equivalent diameter, that is equal to 0. For q average I substitute the correlation: thermal conductivity of the fluid times the difference in temperature divided by the equivalent diameter. Okay, so that is the correlation. And the Nusselt number is given by this Prandtl number, this constant which depends on Prandtl number, times the Grashof number power 1/4, and within this Grashof number I have a temperature difference between the fin and the fluid. Okay. And since I have a temperature difference in the Grashof number as well, it is preferable to define it in terms of a scale temperature, where the scaling is the difference on the surface of the tube and the fluid temperature, T naught minus T f. Okay, so this is T star that is defined. Okay. And based on that I got an equation, okay, for T star power 5 by 4 by L c square, okay, where L c square is given by this value. Okay, L c square, okay, the distance square is given by Ks by Kf into 1 by Grashof number power 1/4, okay, times 1 over Cpr times the characteristic diameter square, equivalent diameter square. Okay. So, therefore, this is the characteristic length. What is the diffusion length in this case? Okay. The diffusion length is Gr naught power minus 1/4 times dE. The diffusion length, if you recall, for natural convection, the diffusion length, diffusion close to the surface is restricted to a distance comparable to the Grashof number power minus 1/4 times the equivalent diameter. Okay. And this is the length scale for the variation of the temperature along the fin. Okay. So, therefore, I can use this balance equation only if LC square is much larger than the diffusion length square. Okay. I can use this balance equation only if LC square is much larger than the diffusion length square. Okay. Alternatively, dE square by 4 into Ks by Kf into 1 by C of PR times 1 by GR naught by 1/4 is much greater than dE square by GR per half. Okay. And the equivalent diameter will cancel out on both sides. Okay. And I require that Ks by Kf, okay, times 1 by C of PR is a factor of 1/4 on the left times GR per half, sorry, GR per 1/4, much greater than 1. Okay, that is the condition, and that condition will almost always be satisfied because the Grashof number is large. I told you it varies between 10 power 4 and 10 power 9, and the ratio of conductivities is large. The fin is being used because it has a high thermal conductivity, and you would expect that the thermal conductivity of the fin is much larger than that of the fluid outside. Otherwise, you would not need to use the fin. Okay. So, this condition is almost always satisfied, and therefore, I can use this balance equation to determine the temperature field along the length of the fin. Okay. So, the balance equation becomes d square T star by dx square is equal to T star per 5 by 4 by LC square. Okay. That is what the balance equation becomes. Okay. And if you recall the configuration of the fin, okay, it was fixed to the wall. Okay, it was fixed to the wall. The temperature was T naught here. Okay. And we had said that the temperature at the other end is TL and this other end is insulated. The fluid temperature is TF. Okay. And we had defined T star is equal to T minus TF by T naught minus TF. Okay. Therefore, if x is this direction, at x is equal to 0, T star is equal to 1. Okay. T minus TF by T naught minus TF is equal to 1. Okay. And at x is equal to L, T star is equal to TL minus TF by T naught minus TF, and I will call this as TL star. Okay. So, you have to solve the equation using these conditions. Okay. You may have dt by dx is equal to 0 also if there is a 0 flux condition on the other side. How do we solve this equation? This is a second order equation with a nonlinear term on the right side. So, the solution is not as easy. I will just briefly tell you how it is solved and then you can try it out for yourself. The way you do it is to write multiply both sides by dt by dx. Okay. You can see that the left side is half d by dx of dt by dx the whole square. Okay. The right side is 4 by 9 LC square dt star per 9 by 4 by dx. Okay. If you take the derivative of t power 9 by 4, you will get 9 by 4 times t power 5 by 4. Okay. And this equation can be integrated once with respect to x, okay, to get that dt by dx whole square is equal to 8 by 9 LC square, okay, t star power 9 by 4, okay, plus a constant. And that constant is determined from the condition that at x is equal to L, okay, t star is equal to TL. That constant has to be determined from that condition. Okay. Therefore, this is I made a mistake here once again. Yeah, no, this is correct. This, this calculation is correct. There is no negative sign here. Okay. So, you can substitute this and then solve it. Okay. I can do a few more steps, but that is not really necessary. From this, we can find out what is the flux at the surface. Okay. So, at x is equal to 0, t is equal to TL, and I said it is insulated. So, dt star by dx has to be equal to 0 at x is equal to L. Okay. So, if that is the case, then the C will be equal to minus 8 by 9 LC square t star L power 9 by 4. Okay, that is a constant of integration. And I just use that to get dt star by dx is equal to 8 by 9 LC square, okay, t star power 9 by 4 minus TL power 9 by 4. Okay. And this is a square here. Okay, this is a square. Okay. I can take the square root of this dt star by dx. Okay. When I take the root, I have to take the negative root. Okay. That is because temperature has to decrease downstream. Okay. As you go along the length, the temperature has to decrease because there is conduction going out. Okay. There is transfer of heat out from the fin. Therefore, the temperature has to decrease, and I will get 8 by 9 LC square t star power 9 by 4 minus TL power 9 by 4. The heat flux at the surface of the fin, the heat flux at the surface of the tube, okay. The heat flux at the surface of the tube, okay. The heat flux at the surface of the tube is what ultimately gets transferred out to the fluid, okay. The flux that is coming at the pipe wall is what is ultimately getting transferred out to the fluid, okay. So, that heat flux, that is Qx at x is equal to 0, okay, is equal to minus k times dt star by dx at x is equal to 0. Okay. This is the Ks, okay. This is the thermal conductivity of the fin. Okay. This is the thermal conductivity of the fin here. Okay. The heat that is coming out from the surface of the fin is what is ultimately transferred to the fluid. So, if you want to find out for this particular fin how much heat is being transferred out per unit time, for a surface temperature T0 at the surface of the tube, you have to take the heat flux at that location, which is the amount of heat that is ultimately transferred out to the fluid. Okay. And I have dt by dx here, and we know that at x is equal to 0, T star is equal to 1, because T star is T minus Tf divided by T naught minus Tf, and T is equal to T0 at x is equal to 0. Okay. So, this is equal to Ks into root of 8 by 9 LC square into 1 minus TL power 9 by 4. And that is the final solution for the temperature, for the heat flux that is being transferred from the pipe wall to the surface of the fin, and that ultimately gets transferred out to the fluid. Okay. So, in this case we have considered natural convection as well as spatially varying temperature field, okay, natural convection as well as a spatially varying temperature field. Okay. And based upon that we have actually managed to obtain an equation for the temperature flux. And the heat flux in the limit where the Grashof number is large, so that the ratio of the characteristic length, okay, and the Grashof and the diffusion length is large. Okay. Whenever the Grashof number is large, the ratio of the characteristic length and the diffusion length is always large, and in that case you can use an approximation. Okay. You can use an approximation that the correlation is the same as what you would have had if the temperature on the surface were a constant. Okay. Even though the temperature is varying, the length scale for variation is sufficiently large compared to the diffusion length over which the temperature changes in the fluid, okay, so that you can use the correlation that was derived for a constant temperature difference between the surface and the fluid. Okay, so this is an example of spatially varying temperature field where you can use a balance equation. And finally, I will go through a last example regarding the heat transfer in a packed column, regarding the heat transfer in a packed column, where basically you have a packing of particles, okay, and there is fluid coming in and fluid going out. The particles are at a high temperature. Okay. It is what is called a phase change material. An example of a phase change material is what is called paraffin wax, for example. It melts at a temperatures in the range of 60 to 100 degrees centigrade. And when the wax melts, the temperature is a constant. Okay. As long as the latent heat, as long as the material has not fully melted, the temperature remains a constant. So, in heat recovery processes, for example, you could have this phase change material in a packed bed, and you could store the energy by passing hot fluid through it, so that it melts at a particular temperature, and then heat a cold stream such that the heat transfer from the wax to the cold stream will freeze it. So, basically you are using this material to store latent heat at that particular temperature. A hot stream is first used to heat it so that it melts, and then a cold stream is used to freeze it so that the heat is transferred to the cold stream, the latent heat, at that same temperature. Okay. So, these are what are called phase change materials, and they actually retain heat, okay, in them. Okay. In this case, we will consider a packed bed with a temperature of the particles is equal to 80 degrees centigrade. Okay. Phase change material with temperature 80 degrees centigrade. 1 centimeter particles. Okay. So, D is equal to 1 centimeter. Okay. And we will consider water flowing through it. Okay. Rho of the fluid is equal to 10 power 3 kg per meter cubed. Okay. Mu of the fluid is equal to 10 power minus 3 kg per meter per second. Okay. And the conductivity of water is 0.6 watts per meter per degree centigrade. Okay. The specific heat is equal to 4.2 into 10 power 3, okay, joules per kg per degree centigrade. Okay. And we consider that water comes in with initial temperature 20 degrees centigrade. The temperature of the paraffin wax is equal to 80 degrees centigrade. Okay. And the outlet temperature, okay, we desire that it should be 75 degrees centigrade. Okay, we desire an outlet temperature of 75 degrees centigrade. So, we want to heat the inlet water stream from 20 degrees centigrade to 75 degrees centigrade. And I will assume a porosity is equal to 0.4. Okay. And what I want to know is what is the length of this bed, okay, an estimate for the length of this bed in order to increase the temperature from 20 degrees centigrade to 75 degrees centigrade. Okay. I will take a particular cross sectional of this bed, okay, delta z at a location z, okay, in the fluid, okay, and consider what is the change in temperature because of the fluid velocity, okay, because the fluid is flowing through this bed, okay. And the fluid velocity, the what is called the superficial velocity, is equal to 10 power minus 2 meters per second, 1 centimeter per second is what I will use for the superficial velocity of the fluid, okay. Now, as the fluid flows through this bed, it gathers some energy from the particles, okay. So, what is the change in energy, okay, per unit time? Per unit time, okay, is equal to rho f Cp into T at x plus z plus delta z minus T at z. That is the change in energy of the fluid itself, okay, times the volumetric flow rate per unit time, okay, times the volumetric flow rate per unit time, okay. So, if the bed has cross sectional area A, okay, the cross sectional area that is occupied by the fluid is going to be equal to A into epsilon, okay. If I take the cross sectional area, okay, the cross sectional area that is occupied by the fluid is going to be equal to A times epsilon, because the porosity is epsilon, and the velocity of the fluid through the particles is going to be equal to the superficial velocity divided by epsilon, okay, the superficial velocity divided by epsilon, okay. So, this is equal to rho f Cpf T at z plus delta z minus T at z times A times Vs, okay. That is the change in energy of the fluid passing through this per unit time. That has to be equal to the heat transfer rate per unit time, okay. That has to be equal to the heat transfer rate per unit time, okay. Is equal to Q average into the surface area of the particles, okay, within this volume, okay. Q average times the surface area of the particles within this volume, okay. Okay, the total surface area of the particles within this volume, okay, and the surface area of the particles, okay, is going to be equal to QAV into the surface area per unit volume times the volume, okay. Note that A is the area, cross sectional area of the bed, okay, whereas AP is the surface area of particles within this distance delta z, okay. Surface area of particles within this distance delta z, right, is going to be, so if we take a volume V, right, if we take a volume delta V, okay, the number of particles within this volume, okay, the number of particles within this volume, okay, is given by the volume of the particles is going to be equal to 1 minus epsilon times delta V, okay. The total volume of the particles within delta V is going to be 1 minus epsilon times delta V, because epsilon is the void fraction that is empty or occupied by fluid. 1 minus epsilon is the fraction that is occupied by particles, okay. 1 minus epsilon times delta V is going to be equal to the number of particles, okay. So, it is going to be volume occupied by the particles divided by the volume of one particle is going to be equal to the number of particles, okay. Therefore, the total surface area is equal to the surface area of one particle, okay, the surface area of one particle times 1 minus epsilon into delta V by Vp. Okay. And if you recall, AP by Vp is 6 by the equivalent diameter. The ratio of volume and area of a particle is equal to the equivalent diameter divided by 6, okay, which is equal to the hydraulic radius. So, I can write this as 1 minus epsilon delta V into 6 divided by the equivalent diameter. Okay. So, that is the expression for a fixed bed. Okay. So, this is the surface area of the particles within the volume delta V. Okay. So, this is equal to 6 into 1 minus epsilon delta V divided by dV. Okay. And delta V in this case is the product of the cross sectional area times delta Z. Okay. So, therefore, if I put these two together, okay, I will get okay, so let me get rid of this. Okay. At the location Z plus delta Z minus T at the location Z, A Vs is equal to minus. Okay. So, in this case I am sorry, it is a plus sign because heat is transferred from the particles to the fluid. So, therefore, there should be a plus sign here, is equal to QAV 6 into 1 minus epsilon A delta Z by dE. Divide throughout by A times delta Z, take the limit as delta Z goes to 0, and I will get rho f Cpf, okay, dt by dz, okay, into Vs is equal to 6 Q average into 1 minus epsilon by dE. Okay. And simplify this. Okay. dt by dz is equal to 6 QAV into 1 minus epsilon by rho f Cpf times dE. And now I use a correlation for the heat flux. Okay. So, the heat flux in this case, if you recall, the correlation for the heat flux, the Nusselt number for a packed bed is defined as Nusselt number is equal to Qa average by K delta T into 1 minus epsilon by dE epsilon. Okay. The characteristic length scale for the particles is equal to the characteristic length scale for the voids is equal to dE into epsilon by 1 minus epsilon for a packed bed. You can go back and refer to this. Okay. So, I can use this as the Nusselt number correlation. And using this, I will get dt by dz is equal to K into T minus T, into the difference in temperature, okay, Ts minus T. Okay. T is the temperature of the particles, the phase change temperature of the particles, into delta T into into d epsilon by that is the average flux. okay, using the Nusselt number correlation for the average flux. Okay. So, this is the Nusselt number correlation for the average flux. That multiplied by 6 into 1 minus epsilon by rho f Cpf dE. Okay. And I can write this as Tp minus T by a characteristic length Lc, okay, where Lc is equal to rho f Cpf Vs dE square. Okay. I think I missed out a factor of Vs here. Okay. Okay, Vs dE square epsilon by 6 Nusselt number Kf into 1 minus epsilon the whole square. Okay, that is the characteristic length. Okay. And you can calculate this characteristic length by substituting all the parameters here. Okay, by substituting all the parameters here. Okay. So, this rho f is equal to 10 power 3 kg per meter cubed. Cpf is 4.2 into 10 power 3 joules per kg per degree centigrade into velocity 0.01 meters per second, okay, into dE square 1 centimeter square 10 power minus 2 meters the whole square into epsilon is 0.4 in this case, okay, divided by 6 into the Nusselt number into 0.6 into 10 watts per meter per Kelvin into the fluid, that is the fluid thermal conductivity, into 0.6 the whole square. Okay. The Nusselt number has to be calculated from a correlation. Okay. The correlation that we will use is that the Nusselt number is equal to the Whittaker correlation into PR power 1/3. Okay. The Reynolds number for a packed bed was defined as rho Vs d by 1 minus epsilon into mu, which is 1.67 into 10 power 2. So, the Reynolds number is approximately 167. The Prandtl number is equal to Cp mu by k. You can just put in the values here and you get about 7. Okay. And this gives us a value of Nusselt number is equal to 23.9. Okay, just substituting the numerical values in this above expression. Okay. And if you substitute all of that here, you will get Lc is equal to 5.4 centimeters. Okay. Okay, so that is the expression for the characteristic length. Okay. And once I have the expression for the characteristic length, I can put that into this equation. Okay. Is equal to Tp minus T by Lc, okay. And therefore, T P minus T is equal to Tp minus T inlet, okay, e power minus Z by Lc is the solution of this differential equation. Okay. And if I substitute Tp is equal to 80 degrees centigrade, okay, initial temperature is equal to 20 degrees centigrade, and the outlet temperature is equal to 75 degrees centigrade, I get the total Z is approximately 13.9 centimeters. Okay. You can do that calculation to get the total length. Okay. So, the point I am making is that the characteristic length in this case was 5.4 centimeters. Okay. The requirement here is that this characteristic length for the change in temperature should be much larger than the particle diameter. Particle diameter was about a centimeter. This characteristic length is about 5 times that. You cannot use this description if the characteristic length is comparable to the microscopic scale. In this case, microscopic scale is a particle diameter. So long as the characteristic length is much larger than the microscopic scale, you can use this description, do a balance over a differential volume, get an equation for the evolution of the temperature field. Okay. Solve that equation to find out what is the total length required. So, this is an example of a packed column where we have used a correlation, in this case the Whittaker correlation, in order to determine the Nusselt number. And once we know the Nusselt number, we have determined what is the evolution of the temperature with respect to distance, and from that we have backed out what is the evolution of what is the length that is required for getting a specific outlet temperature at the outlet, okay, given a temperature at the inlet and given a temperature of the particles over here. So, this is another example where a correlation has been used within a balance equation in order to determine the spatial variation of temperature in a packed column. So, with this I will complete my lectures on using correlations in balance equations, and we will go on to the next topic, that will be spatially and temporally varying concentration or temperature fields, in which there is a variation both in space and time, and we have to solve the partial differential equation. I will continue that in the next lecture. I will see you then.